Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on Taylor series and Taylor polynomials. So far we have discussed that Taylor series are basically a polynomial series representing a smooth function, right? A function that doesn't have singularity at a given point. And then this is basically Taylor expansion is basically a polynomial expansion at a given point, and the coefficients are, the terms are like 1 over n factorial times the nth derivative of the function at the point x0 times x minus x0 to the nth power. All right, and then and this polynomial to some order locally approximates the function, and it has a uniform convergence. It means that if the function doesn't have singularity, the series, the limit when we have infinite terms, it has to exactly match the function. Not only that, because it's a uniform convergence, we can term by term differentiate. So if I want to know the Taylor series of f prime, I calculate the Taylor series of f and take the term by term derivative. All right, and one example was the exponential function e to the x, and at x equals 0, e to the x is sigma n from 0 to infinity x to the n over n factorial, which is 1 plus x to the 2 over 2 factorial plus x to the 3 over 3 factorial, etc. And this has a uniform convergence for any x, right? So even though we're expanding at x equals 0, we can see that if I put, for example, x 100, this series should converge to e to the 100. Furthermore, if I take the derivative from left and right, so the derivative of left, e to the x, d dx is just itself e to the x. And then I can differentiate term by term from the series. So 1 becomes 0, x becomes 1, x squared over 2 is x cubed over 6 is x squared over 2. So eventually I get the same series, right? So it shows that the derivative of e to the x is e to the x, and the derivative of the series is again the same series. And we looked at one way to implementing the Taylor series in or the Taylor expansion in Java, which was the symbolic math library. And then we used the diff method for our symbolic math library that had some basic functions. And then let's go to Eclipse and try to recap on that. So in the sequence project, I have the Taylor expansion class, and here we had a function from our symbolic math project. A function is basically an abstract class that represents an abstract function, right? And we have different types of function, cosine, cotangent, etc. All of them extend this abstract function. And we implemented operator overloading for this function, like add, subtract, multiply, and divide, and negate. So we can use operator overloading for this function. And in the Taylor expansion, we have a method called getSeries, and here we are just creating the result. So basically we're calculating the Taylor expansion at x equals x0, and for n terms, or the degree of the Taylor polynomial is n, okay? And we start with a 0 polynomial, and for the 0th term, it's just the value of the function at x0, okay? There is no derivative. And for higher order terms, we create a copy of the original function, and then the overall polynomial for this ith term, we start with 1, and then we calculate the 1 over n factorial, right? For k equals 0, k less than I, k plus plus. We take the diff recursively, so this calculates the derivative of function I times, and then we also increase the power of x minus x0 by multiplying by itself, and then the factorial is just multiplies by k plus 1, all right? And then we have 1 over factorial times funcopy. Funcopy holds the value of the nth derivative or ith derivative, right? Remember, we have a for loop that runs over I, and times the polynomial x minus x0 to the power of I. Okay, and then we return the result, and we can quickly test it. So here let's just maybe create a test class, test Taylor series, and let's have a main method, and I'm going to invoke test1 here, and we're going to have a public static void test1, and here I'm going to define a function. Let's call this func is and I'm going to I'm going to do a static import, basically symbolic math from if you recall, in the function space we defined methods that return this function. So from function space I'm going to import all the functions we have already defined. Let's also import the function, alright, the symbolic function, and let's call this let's say sine of x, alright, plus cosine of x, or maybe something more fancy like sine of x times sine of x. And then we're going to plot this first. Double x vals is mathutils dot line space from minus math.py to math.py, and let's say 1000, and then double func vals is array func dot apply the real function. T goes to func dot evaluate get value at t, and then apply to the x vals array. And then we're going to have a MATLAB chart, fig new MATLAB chart from mathlib project, and then fig dot plot x vals and func vals. Okay, and then fig dot render plot fig done show with a true flag. And then I'm going to run this, and it doesn't show the figure because I need to go to the run configuration, and in the VM arguments I'm going to remove this check. Alright, so this is x-axis and this is the function. We're plotting sine squared, and alright, now let's try to get the Taylor series around x equals 0. So in order to do that, I'm going to create a Taylor expansion object, Taylor expansion, new Taylor expansion. I'm going to pass our function here, and then I'm going to create a polynomial and Taylor series or series Taylor polynomials, and we're going to call the Taylor expansion get series, and around 0 we're going to have 5 terms, and sys out Taylor series. Okay, so let's run this. We get x5 0, x4, x3 0 again, x2, x0. So as you can see, we only get the even orders, and that makes perfect sense because it acts like a even order root around 0, right? Quadratic or fourth order, so it doesn't have fifth order or third order or first order. And we can also plot this. So double Taylor vals, we're going to apply array function, apply t goes to Taylor series dot evaluate at t, apply it to x vals. All right, and so I'm going to plot the function with color blue, fig dot plot x vals, and then Taylor vals with color red. Yeah, as you can see, the blue one is the function and the red one is Taylor expansion, fifth order. And as you can see, it can approximate the function better. Now if we go to, let's say, 10 terms, and we see that it probably gets so it covers a wider range. And we already know that this sine function is analytic function and it doesn't have any singularity, but so the Taylor series must converge to the entire function at any given point, even though we're expanding it around 0 as we add more and more terms. All right, that's the whole idea of Taylor. But now there's another question about if I expand the function f of x around x0, so I get x minus x0 terms, right? The question is, if I cut it at some point, let's say n terms. Now basically the idea is that if my function has singularities and I expand the function at around some point, how far from this point the series actually converges to the exact value of function. And that defines something called the radius of convergence for Taylor series, or in more general sense for power series. We said that Taylor series has a uniform convergence, which means you can apply term by term algebra. So if I have two functions, f of x and g of x, and both of them at x0 have Taylor series, all right? The coefficients are fn for f of x and the coefficients are gn for gx. Now we can add and subtract Taylor series. So if the Taylor series of f plus g is exactly the same series, the coefficients are fn plus gn. The same thing for subtraction, fx minus gx, the coefficients are fn minus gn. We can multiply or divide by a number. So if I multiply the function by some constant number, the coefficients of the Taylor series get multiplied by the same number, term by term. We can differentiate term by term. So if I know the Taylor series of f of x, the Taylor series of f prime is just differentiating by term for this series, the term. So the coefficients are n fn x minus x0 to the n minus 1, all right? And n starts here from 1. So if I shift it to 0, and then I get n plus 1 fn plus 1 x minus x0 to the n, right? So I can find the coefficients of f prime. But then in the discussion of convergence of the series, we said that if I have a series of sigma n from 0 to infinity of some sequence, because as soon as I plug in some number for x, this becomes a sequence, right? The terms are fn x minus x0 to the n, all right? The necessary condition is that as n goes to infinity, the generating sequence, which is fn or an here, x minus x0 to the n, this sequence must go to 0. The limit of this sequence must go to 0. Okay, and this is very important. And if that's the case, then we can find how far from x0 we can go such that this limit goes to 0. And because this is a power series, if this goes to 0, we are guaranteed that the Taylor series converges. Okay, so we can define a radius convergence, which has the meaning of how far from x0 can we go so that the limit of the generating sequence still goes to 0, so that the series still converges. And we can take the square root of an, nth root of an times x minus x0, all of it to the power of n, okay? And that should remain less than 1 as n goes to 0. So the radius of convergence is 1 over the limit of n goes to 0, square root, the nth root of an. And an is basically 1 over n factorial times the nth derivative of f, right? Here an represents fn or gn. And fn, the coefficients of Taylor series are 1 over n factorial, 1 over n factorial times the nth derivative of the function at the point x0, all right? This tells us how far from x0 can we go so that the power series, the Taylor series, still converges to the value of the function. And typically this is not, and this is called Cauchy-Hadamard theorem, that tells us the radius of convergence for a power series of the form fn or an x minus x0 to the power of n. If an's have the same sign as n goes to infinity, they don't oscillate or change sign, then r is equal to limit of an over an plus 1, the ratio of two consecutive terms. We take that limit. If n's have alternating sign as n goes to infinity, we can define a new sequence bn, which is the square root of an minus 2 minus an minus 1 squared, right? And then r becomes the limit of bn over bn plus 1 when n goes to infinity. All right, so let's try. And the other thing, one of the important things is that r, the radius convergence, can be infinite. All right, that means this limit can go to 0. So typically people evaluate 1 over r, which is this limit of square root of n an. All right, so we can also do that and then invert it. And the meaning of the infinite radius of convergence is that no matter how far we are from, if we write the Taylor expansion for x0, no matter how far from x0 we go, this Taylor series eventually converges to f of x, no matter how far. That's the meaning of the radius of convergence. The problem is that Taylor series have, as we get farther and farther away from x0, the convergence becomes slower and slower, which means we have to add many more terms in order to get a good accuracy or get a good estimation of the function. All right, so let's try to go ahead to Eclipse here, and in our Taylor series class, Taylor expansion class, what we want to do, we want to find the radius of convergence, radius of convergence. So what I'm going to do first, I'm going to create a public sequence. I'm going to create a sequence that basically represents the nth term, the terms of the coefficients of the Taylor series. So we're going to basically get term at double x0 and or maybe let's call this Taylor coefs and int n. All right, so what happens here is basically we want to do the same thing here. So let's look at this for loop, and we are going to evaluate basically at, so I here is the n, we're looking only at the nth term, and then we're going to return n goes to so this so n here is the nth degree. We want to what do we want to calculate? We want to calculate the nth term of the sequence, right, at x0. So we don't need to know the n, right? So basically we're calculating an, the coefficients, or fn. The term is x minus x0 to the nth power, right? So let's call this Taylor coef. And then what we need to do here is we're going to say that return n goes to something. And what is that thing? If n is equal to 0, we're going to return the function at 0, right? And then else we're going to say that, okay, we're going to create a copy of the function, and then basically we're going to eventually return something like this. So let's see, we're going to create a copy of the function, and we're going to calculate the factorial, and then we're going to for k from 0, k less than n, k plus plus, we're going to take the derivative, calculate the factorial, and then we're going to return 1 over factorial, the nth derivative. So we're going to return 1 over n factorial times, alright. Okay, this is how we create the Taylor a sequence that represents the Taylor series, the Taylor coefficients. Alright, so let's go back here. Look at the sequence. So here we calculate the Taylor series of this function, and let's create a sequence Taylor coefs, and or let's just call it Taylor is Taylor expansion dot Taylor coef at x0, which is 0. All right, and let's just sys out Taylor evaluate at 0, and then sys out Taylor evaluate at 1. Let's say we want to see the first 5 terms. 2, 3, 4, 5. 1, 2, 3, 4, and 5. Alright, so let's run this. So also let's make the Taylor expansion 5. So we have so this is the plot. So the 0th term is 0, and then 0, and then 1, and then 0, and then minus 0.333, correct, and then 0. So now we have a sequence that represents the Taylor coefficients. All right, and now what we want to do is find the radius of convergence. So finding the radius of convergence, and the way we're going to do it, we're going to create a new sequence, and then so let's do this here. So I'm going to create a new sequence, bn or b, which, or the rn, radius. This represents the radius, which is n goes to basically math dot pav of Taylor sequence evaluate at n, and raise it to the power of 1 over n, and let's make sure that the n is cast as double. All right, and always be careful. So if I write this as 1 over n, because n is a long and one integer, the result is always 0. So Java compiler interprets it as 0, which is incorrect. So we want to make sure that whenever we write something here, it's 1.0, which already doubles. Or if we write just 1, which will be interpreted as int, we have to make sure that we cast double for n, right? Just make sure that you do that, otherwise you get a wrong answer. Always be careful about how the Java compiler handles integers and longs when we in fact want to have a double value. So this is radius of convergence, sequence, and then let's plot this. So what we're going to do here, I'm going to basically create so let's put this MATLAB thing here, the previous figure, and now I'm going to create a new MATLAB chart, fig new MATLAB chart, and then what I'm going to do, I'm going to create double indices, mass utils, linear space. I'm going to give it a step size. So I'm going to start from 1. Okay, now so I'm going to create new double 100 points, and then double radius vals, new double indices dot length. Alright, and then for int I equals 0, I less than indices dot length, I plus plus, we're going to have indices I equals I plus I, because we want to start from 0, okay? And or I plus 1, doesn't really matter. So, and then radius vals at I is basically, note that indices of is double, but this sequence evaluate, it has to take a long, so we're going to pass in I plus 1. All right, and then now here I'm going to fig dot plot indices and then radius vals, fig dot render plot fig dot show with a true flag. Okay, it's taking time. All right, so maybe let's just look at the 10 terms first. So as you can see, all the odd terms are 0, which we expect. So we have only even zeros, right? And then we are calculating the basically what we are calculating here, this is actually the reciprocal. What we are calculating here is 1 over Rn, because this is equal to limit of an to the power of 1 over n. All right, so what we need to do, we have to basically invert this, and the problem here is that we have zeros, so if we invert this we end up with infinities, right? Yes, so let's stick to, that's one reason that we always prefer to calculate 1 over r instead of 1 over this limit. And then what we want eventually is to have the limit of this sequence. Okay, so if I put 20 here, we see that it takes time to run and does the calculation, because it just have to make more and more take more and more differentiation here. Okay, so it takes time. And it's still taking time. So okay, this is probably not the best approach, but if we look at, for example, the Taylor series 20 terms, what we see, let's run this. Now obviously it's still struggling, so this takes time for the Taylor series to evaluate, but the idea here is that we can find the inverse of the radius of convergence by looking at the square root of the nth root of an. Okay, now we know that for the sine function, all the coefficient basically, if we look at the, for example, the terms, let's put this back here one more time. What we do know here is that, for example, if I calculate for the nth term, and I actually have to take the absolute value here, absolute value of the Taylor. Okay, and all the coefficients are positive for the sine squared. So what we can do, and it is obvious that this sequence is converging to 0, and when it converges to 0, and remember this is 1 over radius of convergence, it means that radius of convergence is infinite. So we can, if we are expanding around x equals 0, we can be infinitely away from 0, and the Taylor series still should converge to the original function. But but then it has a slow convergence, so we have to add many terms, all right? However, so here we have we have a sequence an which basically doesn't change sign. So what we need to do is that we can use this definition, an over an plus 1. So so instead of doing this, I'm going to create a new sequence. Let's call this radius, and goes to Taylor evaluate at n divided by Taylor evaluate at n plus 1. All right, and now let's look at this sequence. So the problem here is that we have alternating every other term coefficient of the sequence is 0, so this is basically not a good way of calculating the radius of convergence. Okay, because if n is even, n plus 1 is odd, and all the odd terms are 0. But let's say we look at the x equal 1 instead of x equals 0. And then we try to evaluate this sequence. And as you can see, it's oscillating. So we don't have actually a positive sequence, it's oscillating. So we need to do the sequence b, which is n goes to math dot square root of math dot abs Taylor evaluate at n minus 2 times Taylor evaluate at n minus 1 n minus 2, so n minus 2 times n minus Taylor dot evaluate at n minus 1 times Taylor evaluate at n minus 1. Okay, so we end up with this sequence b, and then we try to calculate bn over bn plus 1. So let's say it's radius again. Let's comment this. N goes to b evaluate at n divided b dot evaluate at n plus 1. And let's see what happens now. Okay, so as we see, this is going to infinity, growing. That means the radius of convergence is going to infinity, which means the radius of convergence of the sequence is basically infinity. Okay, but if I add something like sine squared over x minus 2, for example, then we have a singularity at x equals 2. Then the question is, we should be able to get a radius of convergence when we expand around 1 of just 1, right? We can only go from 1 to 2 until we hit the singularity. So let's see what happens in this case. Now calculating the radius of convergence takes the Taylor coefficients takes time, because we're using our symbolic function, so we're taking a lot of derivatives. But let's just wait. And but again, the idea here is that if we are expanding the Taylor series around a given point, the radius of convergence is the distance from the point to the closest singularity of the function. Here we have x equals 2. So the radius of convergence is 1, going from 1 to a maximum of 2. All right? As soon as we hit the singularity, the Taylor series starts to diverge. So it doesn't converge to the function again. So this one is still calculating, so it takes time, even for 10 terms. Okay, it's still calculating. Alright, I'm going to stop this because this is taking too long, but this was the whole idea of the radius of convergence for Taylor series. I hope you enjoyed this lecture. Please stay tuned. I have more lectures to come, and I hope you enjoyed this video, and thank you, and I'll see you in the next one.